Okay, so in this video we'll talk about two more tests that we can use to test a series for convergence or divergence. They're called the ratio test and the root test, as you can see in this title slide. And to begin, we're just going to do a brief refresher on geometric series. Right? These series you've seen before, and we know exactly when these series converge. Right? It's when the common ratio in absolute value is less than 1. So for instance, this series is 2 plus 6 over 5 plus 18 over 25, and so on. And it says first term 2, common ratio 3/5. So since r is less than 1 in absolute value, this series converges. In fact, we know exactly what it converges to, although it's not going to be relevant to what we're going to talk about in this video. It's a over 1 minus r. But just as a review, right, that's the sum of this series. Now, why am I starting with the geometric series here? Well, it's mainly to point out that this ratio here of the series, term to term, determines convergence. Right? So in other words, since we know that each term in your series is simply 3/5 of the previous term, then that's enough to tell us it's convergent. Whereas if you had a geometric series where something like this, for instance, 1 plus 1.1 plus 1.1 squared plus 1.1 cubed, and so on. Well, from term to term, they're getting larger and larger because you're multiplying by a ratio that's larger than 1. And this is divergent. So it turns out we can apply a similar idea to series in general. And by that I mean, if we can get an idea of what this ratio looks like for a series as n goes to infinity, then maybe that can also help us determine whether it's convergent or divergent. And you're probably thinking, well, for any series that's not geometric, this ratio, that's not going to be the same from term to term. Right? That's what makes this specific series on this slide geometric, because the common ratio is the same. So how are we going to do this analysis for general series? Well, it turns out we just need to take the limit of the ratio. And what the ratio test says is, if you take this limit, it's an plus 1 over an. Right, the n plus first term over the nth term. As n goes to infinity, if you take the limit of the absolute value, if that limit is less than 1, then it's a very strong result, actually. It gives you absolute convergence for your series. If the limit is larger than 1, or if the limit is infinity, then it's divergent. The partial sums grow fast. Finally, what if this limit is exactly 1? Well, this is a special case here for the ratio test, because the ratio test does not actually tell us anything in that case. Right? And in other words, it's inconclusive. No conclusion here. So I'll give you an example of how we can apply the ratio test to more general series. So again, for geometric series, it's pretty clear. Right, your common ratio here, an plus 1 over an, is equal to 3/5 for all n. So when you take the limit of this, as n goes to infinity, well, it's just going to be 3/5, because it's always 3/5. If that's less than 1, Therefore, the series is absolutely convergent. So how about these ones? N factorial over e to the n. Also n squared minus 1 over n cubed plus 1. Okay, let's work on the first one here. This is the series sum an, where a sub n, the nth term, is n factorial over e to the n. So let's evaluate that limit. N goes to infinity of the absolute value of their ratio. Okay, so let's do it here. What's a sub n plus 1? Well, we have a formula for a sub n. It's here. So a sub n plus 1 is really that same formula, but you're plugging in n plus 1 instead. Then you're dividing by an. Right, so I'm doing it this way so I don't get a very big fraction, fractions inside. Right, but this means this is the numerator, this is the denominator of this big fraction. But now I can simplify. What happens if I divide fractions? Same thing as multiplying by the reciprocal. And here you'll see that terms actually cancel out. E to the n cancels with e to the n here, leaving you with just e to the first power. N factorial cancels and just leaves you with n plus 1 here. And so as n goes to infinity, we're really just taking the limit of n plus 1 over e. And as n goes to infinity, this goes to infinity as well. Therefore, this original series here, by the ratio test, is divergent. Right, so I can write the conclusion here. Diverges by the ratio test. Okay, how about the second one here? So I'd like you to try it yourself. Pause the video right now and try to use the ratio test. Okay. What did you get? Well, let's see what you would have gotten. Evaluating the same limit, a sub n plus 1 over a sub n. So a sub n plus 1 is what you get when you plug in n plus 1. And you divide by a sub n. And so what are we going to do here? Oh, wait. I did the reciprocal already, but I'm multiplying still. I mean, I'm dividing still, so I'm dividing by n squared minus 1 over n cubed plus 1. Now this is the same thing as rearranging terms, this expression. And this looks like we're taking the limit of a rational function. I mean, we are taking the limit of the absolute value of a rational function. In fact, your numerator and denominator, they have the same degrees, right? They're fifth degree polynomials. So that's telling me that I'm going to get some finite limit in between 0 and infinity. And it's probably going to be 1, because I don't see any leading coefficients here for my large powers. So let's see whether that's true. So what I'm going to do is I'm going to factor out the largest power of n I see in each of these terms. N plus 1 squared is really n squared. That's the largest term. So I'm going to factor out n in each of these squared terms. get something like this. And I'm multiplying that by 1. Well, the n cubed is factored out here. 1 plus 1 over n cubed over. And same thing for the denominator. N cubed is the largest. 1 plus 1 over n cubed plus 1 over n cubed. Okay, now things will cancel. The n squareds cancel. The n cubes cancel. And this limit is equal to 1 plus 0 minus 0 over 1 minus 0, 0. The limit is just 1. Therefore, in this case, the ratio test does not tell you anything. All that work, huh? It's inconclusive. In fact, had you seen it was a rational function from the get-go, it would have been a good idea to use another test. Let's say maybe a comparison test. But I'll let you decide that on your own. Suffice it to say that the ratio test here does not actually give you any useful information. And this will always happen whenever you have something rational or algebraic. Now, if you go back to our geometric series, well, another way you can frame this is by looking at, again, the common ratio being, right, it's that number you're multiplying to each term to get to the next term. Which means by the time you're adding the nth term a sub n, it's the common ratio raised to the nth power. Maybe n minus 1. Maybe n minus 2, whatever, it's on the order of n. And so another way we can look at this is by taking the nth root of each term. The nth root here is 3 over 5. Here it's 1.1. And this nth root being larger than 1 or smaller than 1 actually gives you convergence or divergence. And that's the root test. Applying the same idea to general series, it turns out that when you take the nth root of this a sub n formula that you have in absolute value, it's the same as the ratio test. If that limit is less than 1, it's absolutely convergent. If that limit is larger than 1 or infinity, then it's divergent. Same thing, if it's 1, then it's inconclusive. And I guess we can do a simple example here. Well, clearly, if your function has a 1 over n, right? If your formula for your series has 1 over n, I mean, no, not 1 over n, but n, raised to the nth power, then the root test is going to be useful there. Because here a sub n is this whole thing. So the limit as n goes to infinity of the nth root of the absolute value. Right, so the nth root is raising it to 1 over n. That's just the same thing as the limit of this thing inside, right? Because these things cancel. And this is just 1/2. I mean, no, this is actually 0. N squared, yep, that's 0. And so here, the series is absolutely convergent. So the root test is, I would say, less applicable than the ratio test, because you're introducing this 1 over n exponent to your a sub n term. And if your term did not have an n in the exponent to cancel with, then you might actually be making that limit more complicated to evaluate when you add that 1 over n power. But the ratio test is nice. right? I'd say that it applies to more series than the root test. And we're going to be using the ratio test a lot when we get to power series as well.